Good morning students. In today's class we are going to look into the unit Chemical Bonding and Molecular Structure, 4th unit. Before going into the introduction, first we will see what is chemical bond. Suppose if you are shaking hands with someone and if you are holding the hand strongly, this indicates a strong attraction between the two persons. Similarly, if a attraction between the oppositely charged ions is stronger, then it makes a strong bond. In this picture, it shows a strong bond, a sigma bond formed between the overlap of two p orbitals. And this picture shows a weak pi bond formed between the overlap of two p orbitals. So now we are going to look into the chapter Chemical Bonding and Molecular Structure. Matter is made up of similar or different elements or substances. So example, hydrogen, nitrogen, which contains same elements. And if you consider the examples like carbon dioxide, water, which contains two different elements. Substance consisting of same atom is called an element. What is an atom? The smallest particle of matter which may or may not has independent existence but takes part in a chemical reaction is called an atom. So atom is nothing but it is a smallest particle of matter which may or may not has independent existence but takes part in a chemical reaction is called an atom. So in general, atom, except noble gas, it exists in combined form in nature. From atomic structure, atom is a basic unit of matter that consists of a nucleus surrounded by electrons. Atom does not exist independently except in the case of noble gases. An atom contains a positively charged nucleus. The nucleus contains proton and neutrons, and the electrons revolve around the nucleus. What is a molecule? The smallest particle of matter with independent existence is called a molecule. A group of atoms existing as one species having same properties is known as molecule. So we can have two or more definitions for a molecule. So a molecule is nothing but a group of atoms existing as one species having same properties is known as molecule, or a molecule may have similar or different atoms combined together. Can you tell some examples for molecule? The examples are water, H2O. Here it contains two hydrogen atoms and one oxygen atom, and ethane, C2H6. So now we are going to look into the concept chemical bond. What is a chemical bond? How a chemical bond is formed? The force of attraction which holds various constituents, atoms, molecules, ions, etc. together in different chemical species is called a chemical bond. Chemical bond is nothing but the force of attraction which holds the various constituents together in different chemical species is called a chemical bond. So example, in water molecule and ethane, we are having a covalent bond is present between the atoms. Why an atom combines to form a molecule? What is the reason for atoms combine to form a molecule? The first reason is to attain stability. How to attain stability? The stability can be attained by decreasing the energy content of the system and by attaining octet configuration. So all atoms combine to form molecules except noble gas. So noble gas, they exist as independent atoms. Helium, neon, argon, krypton, xenon, radon, they are called as noble gases. Noble gases are called as inert gases. They neither chemically combine with any other element nor among themselves due to stable octet configuration. They are chemically inert. They will not react with any other element or among themselves due to the stable octet configuration. Why an atom combines to form a molecule? What is the reason to form a molecule? Experimentally, it has been found that the magnitude of new attractive force is more than the new repulsive force. So when atom combines to form a molecule, there exists an attractive force as well as a repulsive force. The new attractive force is higher than the new repulsive force. As a result, the two atoms approach each other and potential energy decreases. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and the system acquires minimum energy. For example, energy is released when a bond is formed between two hydrogen atoms. The hydrogen molecule is more stable than that of the isolated hydrogen atoms. So, if a hydrogen molecule is formed by combining two hydrogen atoms, the energy is released when a bond is formed. The energy released is 43,508 joules. So when you plot the potential energy against the internuclear distance, the potential energy decreases when the two hydrogen atoms combines to form a hydrogen molecule, and there exists a maximum overlap between the two hydrogen atoms. The internuclear distance is 74 picometer in the case of hydrogen molecule, and the energy released is minus 436 kilojoules per mole. So can you tell matter is made up of dash types of elements? So matter is made up of same or different types of elements. What is an atom? So atom is the basic unit of matter. How an atom combine to form a molecule? By decreasing energy. Can you tell which one of the following does not form molecule? Halogens, chalcogens, alkali metals, noble gases. The answer is noble gases because they are chemically inert and they have the octet electronic configuration. So now we are going to see why the noble gases are inert in nature. The reason is their outer shell contains either 2 or 8 electrons. So now we are going to look into the atomic number and electronic configuration of the inert gases. So starting from helium. Helium atomic number is 2, it contains 2 electrons. The next member is neon, the atomic number is 10, the electronic configuration is 2,8. The third member is argon, the atomic number is 18 and the electronic configuration is 2, 8, 18. The fourth member is krypton, the atomic number is 36 and the electronic configuration is 2, 8, 18, 8. And the next member is xenon, atomic number is 54 and the electronic configuration is 2, 8, 18, 18, 8. And the last member is radon, atomic number is 86 and electronic configuration is 2, 8, 18, 32, 18, 8. From this we can see the outermost shell contains 8 electrons from neon to radon and 2 electrons in helium. Why molecules are more stable than individual atoms? Because they possess less energy. So how do atoms combine? The atom combine together in order to complete their respective octet so as to acquire stable inert gas configuration. So why the atoms combine with each other? In order to get a octet or stable inert gas configuration. So what is the reason why certain atoms combine while certain others do not? Why do atoms possess only certain combinations? Why do molecules possess definite shape? To answer these questions, different theories have been given from time to time. So can you tell what is the number of outermost electrons in the noble gas? The answer is either 2 or 8. Now we are going to look into the theories on the formation of molecules. The first approach is called the empirical approach, that is by observation. It was given by Coastal-Lewis approach in the year 1916, and the second approach is valency shell electron pair repulsion theory, VSEPR theory, which is formed in 1940. The second approach is the quantum approach. Under quantum approach, the first method is the valency bond theory proposed in the year 1927. The second one is the molecular orbital theory proposed in the year 1932. Now we are going to look into the types of chemical bonds. The chemical bonds are classified into 3 types: ionic bond, covalent bond and metallic bond. The covalent bond again classified into 2 types: polar covalent bond and non-polar covalent bond. Now we are going to look into the Coastal-Lewis approach to chemical bonding. In 1916, 2 scientists, Coastal and G.N. Lewis, explained the chemical bond in terms of electrons. They pictured atom in terms of a positively charged kernel, and and outer shell electrons that could accommodate maximum of 8 electrons. Here they considered a kernel. What is kernel? Kernel is nothing but the nucleus and the inner core electrons are called as kernel. The nucleus and the inner core electrons are called as kernel, and the outer shell electrons that could accommodate a maximum of 8 electrons. So kernel means nucleus plus inner shell electrons, core electrons. Now we are going to look into the octet rule. According to this, atom can combine either by transfer of valency electrons from one atom to another or by sharing of valency electrons in order to have an 8 electrons in their valency shell is called octet. This is known as octet rule. So what is octet rule? The atoms, when combined with each other, they either transfer the valency electron from one atom to another or they share the valency electrons so that 8 electrons will be present in their valency shell. It is called octet rule. So now we are going to look into the example of the formation of chlorine molecule. So chlorine molecule is formed by the combination of 2 chlorine atoms. Can you tell the valency, how many valency electrons are there in chlorine? The valency electrons in chlorine is 7. So now each chlorine is having 1 electron shortage in order to get the octet configuration. Now the 2 chlorine atoms combine with each other and they mutually share 1 electron each. And a chlorine-chlorine single bond, a covalent bond is formed between the 2 chlorine atoms. Now both the chlorine atoms acquires an octet electronic configuration. And this diagram is shown here. So each chlorine atom is having the configuration of 2, 8, 7. So the valency shell contains 7 electrons. So now each chlorine mutually share 1 electron with each other to get an octet configuration of 2, 8, 8. The next example is NaCl. Can you tell what is the electronic configuration of sodium? The electronic configuration of sodium is 281 and that of chlorine is 287. So if you consider here, the sodium is having 1 electron more than the octet configuration and chlorine is having 1 electron shortage of the octet configuration. So in this case, there is a transfer of electron from sodium atom to the chlorine atom. So 1 electron, it gets transferred from sodium atom and the electron is accepted by the chlorine atom. Now the sodium atom becomes Na plus ion with a configuration of 2, 8 and chlorine atom becomes Cl minus ion with a configuration of 2, 8, 8. This transfer of electron from one atom to another and the 2 ions come closer to form a bond is called ionic bond or it is called electrovalent bond. So can you tell what is the meaning of octet? So octet means having 8 electrons. Now we are going to look into the important topic, Lewis symbol. How to draw the Lewis symbol of an element? In the formation of the molecule, the most important criteria is only the outer shell electrons take part in chemical combination and they are known as valency electrons. So during chemical bond formation, only valency shell electrons take part in a chemical combination. They are called as valency electrons. The inner shell electrons, they will not take part in the bond formation. Only the outermost valency shell electrons are involved in bond formation. The inner shell electrons are well protected and these are generally not involved in the bond formation. G.N. Lewis, an American chemist, introduced simple notation to represent the valency electrons in an atom. These notations are Lewis symbols or Lewis dot structures. So the Lewis dot structure for some of the elements are shown in this diagram. It is very simple. So based on the number of valency electrons, you should keep that many dots around that symbol of that element. For example, hydrogen, you know that hydrogen is having one valency electron. So around hydrogen, you keep one dot. Helium, two valency electrons. So we are going to keep two dots. Lithium, one electron, one dot. Beryllium, two electron, two dot. The dots you can keep in any place around this atom. Then boron, three valency electrons, three dots. Carbon 4, nitrogen 5, oxygen 6, fluorine 7 and neon 8. So neon is having a octet electronic configuration. Similarly for sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Just keep as many dots as the valency electrons in an element. The number of dots around the symbol represents the number of valency electrons in an atom. Now we are going to see what are the steps involved in writing the Lewis dot structure. First step is to determine the total number of valency electrons available in a molecule. For anions, each negative charge would mean addition of one electron and vice versa. So suppose if a anion is present, so we have to assume, we have to consider one additional negative charge. Figure out how many octet electrons the molecule should have using the octet rule. Subtract the valency electrons from octet electrons. Divide the number of bonding electrons by 2 to get number of bonds. Organize the atom so there is a central atom. Which atom should be considered as a central atom? The atom, usually the least electronegative atom is taken as the central atom and it is surrounded by other atoms. The central atom can have up to 4 other atoms connected to it. Complete the octet around each of the outer atoms. If there are not enough electrons to complete the octet, the skeleton structure is incorrect. Try a different arrangement. Place remaining electrons around the central atom. So can you tell the number of Lewis dots in chlorine atom? The answer is 7 because the valency electrons in chlorine is 7. So now we are going to look into the examples of Lewis dot structure. Now we are going to draw the Lewis dot structure of carbon monoxide molecule. What is the first step? First we have to calculate the total number of electrons in carbon monoxide molecule. Total number of valency electrons in carbon monoxide. So can you tell what is the valency electrons in carbon? The number of valency electrons in carbon is 4 and the number of valency electron in oxygen is 6. So the total number of valency electrons in carbon monoxide is 10. The second step is to write the skeletal structure of carbon monoxide. So the third step is to put a single bond between carbon and oxygen. That is one shared pair of electron between carbon and oxygen. So now 2 electrons are present between carbon and oxygen atom by making a bond. Now we are left with 8 electrons. So now this 8 electrons can be written as 3 lone pairs on oxygen to complete its octet and 1 lone pair on carbon. So now can you look into this? It is given in this diagram and if you see here, the carbon is not having its octet. It's not completed its octet, only oxygen have completed its octet. So this arrangement is wrong. Then we have to go for the next arrangement. How to arrange the electrons around carbon and oxygen. As in this previous structure, the octet of carbon is not complete. Hence, multiple bonding is required between carbon and oxygen. In the previous case, we have put a single bond between carbon and oxygen, but this could not complete the octet of carbon. So to complete the octet of carbon, triple bond is required between carbon and oxygen. So now we are going to shift the 2 lone pairs on oxygen as shared pair between carbon and oxygen so that octet of both carbon and oxygen remains complete. So now can you rearrange this? So now you put 3 shared pair of electron between carbon and oxygen. So a triple bond is formed between carbon and oxygen. So 6 electrons are involved in this triple bond. Remaining how many electrons are there? 4 electrons. So place 2 electrons around oxygen and 2 electrons around carbon. Now if you see here, each element completes its octet. Carbon is now having 8 electrons and similarly oxygen is having 8 electrons. So the structure is C triple bond O. So the next example is we are going to draw the Lewis dot structure of carbonate ion. Can you tell what is the formula for carbonate ion? Carbonate ion is CO3 2-. What is the first step? First we have to calculate the total number of electrons present in carbonate CO3. First in CO3. In carbon, the total number of valency electron is 4 and oxygen it is 6, and here we are having 3 oxygen, so multiply by 3. Then 6 into 3 is 18. So in oxygen we have 18 valency electrons and in carbon we have 4 valency electrons. The total number of valency electron is 22 in CO3. But the formula given for us is CO3 2- ion. Since it is a negative ion, 2 negative charges present. Now we have to add 2 more electrons. So the total number of electrons is 24. Is it clear? Why we have to add 2 electrons extra? Because it is an anion. So it is having 2 negative charge. So we have to add another 2 electrons. So the total number of valency electrons in carbonate ion is 24. So now we are going to draw the skeletal structure of carbonate ion. As you already know, the valency of carbon is 4. So here we have 1 carbon atom and 3 oxygen atom. So then try to make a single bond between carbon and oxygen. So now you know that carbon valency is 4. That means one of the bond, it should be a double bond. So the one bond between carbon and oxygen should be a double bond. So we can write this structure as C double bond O, single bond O, single bond O, 2-. So that is the skeletal structure of carbonate ion. So now we are going to put the shared pair of electrons between each carbon and oxygen, and then we are going to complete the octet. So as we have already told, there is a double bond between 1 carbon and oxygen. So the carbon, above that carbon we are going to write 1 oxygen. Between these carbon and oxygen there are 2 shared pair of electrons, and between the carbon and oxygen 1 shared pair, and between the carbon and other oxygen 1 shared pair is there. So totally 8 electrons are present in the bond. So now we are going to place the remaining electrons. So if you take the oxygen on the left hand side, so already 2 electrons are present in the carbon and oxygen bond. So in order to complete the octet, how many electrons we have to put on oxygen? 6 electrons. So you put 6 dot on the oxygen which is on the left hand side. Similarly, the oxygen which is on the right hand side, already 2 electrons are present in the bond between carbon and oxygen. Now we have to write 6 dots on the carbon on the right hand side to complete the octet. Now if you consider the center oxygen, now there is a double bond between carbon and oxygen. Already 4 electrons are present in this double bond. The remaining is only 4 more electrons. So keep 4 dots over the oxygen atom. So now the octet is completed for the oxygen atoms as well as for carbon. So this is the Lewis dot structure of carbonate ion. So now we are going to consider the Lewis dot structure for some of the molecules like hydrogen molecule. How can you write hydrogen molecule? Each hydrogen is having 1 valency electron. So each hydrogen share 1 electron between each other. So H, 2 dots H. So that is the structure for the hydrogen molecule. Then we have water. So you know that water contains 2 hydrogen and 1 oxygen atom, and 2 electron pairs are present, two electrons are present between hydrogen and oxygen, and another two electrons are present between the hydrogen and oxygen bond. So now 4 electrons are distributed in the two covalent bond. The remaining is only 4 electrons which should be presented on oxygen. So now the octet of oxygen is completed. Then CCl4 molecule, you know that chlorine is having 7 electrons, and you keep carbon, and around carbon 4 chlorine atoms, and you write 2 electrons between each carbon and chlorine. A single bond is formed between carbon and chlorine, so you write 2 electrons between each carbon and chlorine. So now the remaining is only 6 electrons for chlorine molecule to complete the octet. So write 6 dots over each chlorine atom, then the octet is completed. So the next one is nitrogen molecule. You know that nitrogen has the valency of 5. So 2 nitrogen combines to form nitrogen molecule. So the total number of valency electron is 10. As you know that nitrogen makes a triple bond with another nitrogen atom. So we write 3 shared pair of electrons between nitrogen and nitrogen. So now totally 6 electrons are involved in this triple bond. The remaining is only 4 electrons. So put 2 dots on each nitrogen atom. Then now each nitrogen is completing its octet, and a triple bond is formed between 2 nitrogen atoms. So in the same way, we have to write the Lewis structure for the other molecules like BeCl2, PCl5, etc. So if you write the electron dot structure for BeCl2, you know that while writing this electron dot structure of BeCl2, the octet of beryllium is not completed. So now a shared pair of electron is placed between beryllium and chlorine to form a chemical bond. Around beryllium 4 electrons are there, and around chlorine, each chlorine got 8 electrons. So now the beryllium is having shortage of 4 electrons, so it is having less electron than octet. So if you considered PCl5, so between phosphorus and each chlorine atom, 2 electrons are present to make a chemical bond with phosphorus and chlorine. So if you count the number of electrons around phosphorus, so totally it contains 10 electrons. So that means it is having 2 electrons more than octet. So it is having excess electron than octet, and beryllium chloride is having shortage of electron than octet. And carbonate ion, it has the exact 8 electrons. Now we are going to look into the next topic, the formation of a covalent bond. What is a covalent bond? A covalent bond is formed by equal contribution and mutual sharing of electrons between 2 atoms to complete their electronic configuration. So a covalent bond is formed by mutual sharing of electrons between 2 atoms to complete their electronic configuration. So examples are hydrogen molecule, water, carbon dioxide, chlorine, nitrogen, etc. In hydrogen, 2 hydrogen atom combine and each share 1 electron each, and a covalent bond is formed between hydrogen and hydrogen. In 1919, Langmuir refined the Lewis postulation by abandoning the idea of stationary cubical arrangement of octet and by introducing the term covalent bond. So between 2 chlorine atoms, a covalent bond is formed by a mutual sharing of electron between the 2 chlorine atoms. So now both the chlorine atom gets the argon configuration. Here no metals are involved in covalent bond formation. A covalent bond can be a single bond, double bond, and triple bond. So what is a single bond? When 2 atoms share 1 electron pair, they are said to be joined by a single covalent bond. So only 1 pair of electron is shared between 2 atoms, then a single covalent bond is formed. Examples are H2O, methane, ammonia, etc. So in methane, each carbon and hydrogen one shared pair of electron is present, and hence a single bond is formed between carbon and hydrogen. Double bond. When two atoms share two pairs of electron, the covalent bond formed between them is called a double bond. Example is carbon dioxide. Between carbon and oxygen, two shared pair of electrons are present. A double bond is formed between each carbon and oxygen. So another example is ethylene C2H4. A double bond is formed between two carbon atoms. So, triple bond. When combining atoms share three electron pairs, a triple bond is formed. When three pairs of electrons are shared between two atoms, a triple bond is formed. Example is nitrogen and acetylene CH triple bond CH. Can you tell which type of bond is present in nitrogen molecule? A single bond, double bond, triple bond, coordinate, covalent bond? The answer is triple bond. So now we are going to look into the limitations of octet rule. What are the limitations of octet rule? In some compounds, the number of electrons surrounding the central atom is less than 8. We have already seen this with an example of beryllium chloride. The central atom is having less than 8 electrons. This is especially the case with elements having less than 4 valency electrons. Examples are LiCl, BH2, BCl3. Lithium, beryllium and boron have 1, 2 and 3 valency electrons only. Some other compounds are AlCl3 and BF3, which are on shortage of 8 electrons. In some cases, odd electrons are present. So now we are going to look into the examples for odd electron molecules. The molecules with an odd number of electrons like nitric oxide or nitrogen dioxide, the octet rule is not satisfied for all that atoms. So in the case of NO, so we know that the valency of nitrogen is 5 and that of oxygen is 6. A double bond is formed between nitrogen and oxygen, and 3 dots are present over nitrogen and 4 dots over the oxygen. So now the octet rule is not satisfied. In some elements, the octet is expanded, which is called expanded octet or exceeded octet. The elements from 4th period of the periodic table have, apart from the ns and np electrons, it also contains n-1 d orbitals in the case of d block and n d orbitals in the case of p block elements available for bonding. In some of the compounds, the central atom has more than 8 electrons. This is termed as expanded octet. So from the 4th period, in addition to ns and np electron, d orbitals is also available for bonding. And some compounds, the central atom has more than 8 electrons. This is called as expanded octet. Some molecules with expanded octet are given here. PF5. In PF5, the phosphorus, the central atom, contains 10 electrons. Another example is SF6. So the central atom sulfur has 12 electrons. IF7, iodine has 14 electrons. XeF2, xenon has 10 electrons. XeF6, XeO4, etc. In the case of H2SO4, there are 12 electrons around the sulfur atoms. Now we are going to look into the next topic, formal charge. So how to calculate the formal charge in a given molecule. First we will see what is formal charge. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valency electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. So now what is formal charge? It is the difference between the total number of valency electrons of that atom in isolated state minus the number of electrons assigned to that atom in Lewis structure. The formula to calculate formal charge is total number of valency electrons in the free atom minus the total number of lone pair of electrons minus half into the total number of bond pair of electrons. So that will give you the formal charge of the atom. So now we are going to consider ozone molecule, and we are going to write the Lewis structure of ozone molecule. So ozone contains 3 oxygen atoms. So we are going to name that as oxygen 1, 2 and 3. And the oxygen atom 1 and 2 is having a double bond, and the oxygen 2 and 3 is having a single bond. Now to complete the octet, the oxygen 1 atom is having 4 electrons or 2 lone pairs, and oxygen 2 is having 2 electrons, and oxygen 3 it is having 3 electron pairs on the oxygen 3. Now we are going to calculate the formal charge on oxygen atom 1, which is at the left hand side. So what is the formula? Total number of valency electrons minus the number of lone pair electrons minus half the number of bond pair electrons. So can you tell what is the valency electron of oxygen? The valency electron of oxygen is 6. So minus, now we have to subtract the number of lone pairs. So can you tell on oxygen 1 how many lone pairs of electrons are there? So 2 lone pairs, so 4 electrons are there. So 6 minus 4 minus half into the number of bonded electron pairs. So between oxygen 1 and 2 we have double bond. So in a double bond how many electrons are there? 4 electrons are there. So half into 4. So that is 0. So the formal charge of oxygen 1 is 0. So now we are going to calculate the formal charge on the middle oxygen 2. So again the valency electron is 6. So now the oxygen 2 has only 1 lone pair. So we have to subtract 2 electrons minus half into the number of bonded electron pairs. So the oxygen, middle oxygen, it is surrounded by 3 bond. 1 double bond on left hand side and a single bond on right hand side. So totally 6 electrons are present in the bond. So now the formal charge on the middle oxygen is +1. Now we are going to calculate the formal charge on the third oxygen, which is at the right hand side. So again 6 minus. So now the third oxygen is having 3 lone pairs. So totally 6 electrons are present. So 6 minus half into number of electrons in bonded pair. So here only 1 bond, a single bond is there. So minus half into 2. So the formal charge is -1. So how to write the formal charge of this ozone molecule? So left hand side the charge is 0. Middle one is +1. The terminal oxygen -1. Now we are going to look into the resonance structure. So what are resonance structures? How to write this resonance structures? So now we have written the Lewis structure of oxygen in the previous example. A double bond is formed between the first and the second oxygen, and a single bond is present between the second and the third oxygen. But we can also write in this manner also. The first and the second oxygen gets a single bond, whereas the second and the third oxygen gets a double bond. There are 2 ways of writing the structure of ozone molecule or Lewis structure of ozone molecule. So by this way we are getting 2 structures. So now these 2 structures are called as resonating structure. So now the resonating structures are represented by a double-headed arrow. So between these 2 structures, put a double-headed arrow. The first one is called as the resonating structure 1. The second one is called as the resonating structure 2. So which is called as canonical forms or contributing structures. So now we can write a hybrid of this canonical structure. What is a hybrid? So that is in structure 1, the double bond is present between the oxygen 1 and 2. In structure 2, a double bond is present between oxygen 2 and 3. So a double bond is present on the left hand side as well as on the right hand side. This we can write by writing a dotted line on both the sides, both left hand side and right hand side. So now between the oxygen atom, now we are going to represent a dotted line. This indicates the oxygen, the 2 oxygens are connected by a double bond on both the sides. So the structure 3, which is called as the resonance hybrid. So the resonance hybrid is having less energy compared to the two canonical forms or contributing structures. The canonical forms are unstable, whereas the resonance hybrid is more stable because it is having less energy. So this is called resonance energy. Now we are going to write the resonance structure for carbonate ion and the formal charge on carbon atom. So we have already studied how to write the Lewis structure for carbonate ion. So we have written a single bond between carbon and oxygen on left hand side and the right hand side, and the middle one has a double bond between carbon and oxygen atom. Now we are going to calculate the formal charge on carbon atom. As you know, the valency of carbon is 4 and the carbon is not having any lone pair of electrons, so it is 0 minus half into the bonded pair of electrons. Now the carbon is having 4 bonds, 1 double bond and 2 single bonds, totally 4 bonds. In 4 bonds 8 electrons are present, so half into 8, that is 4 minus 4, that is 0. The formal charge on carbon is 0. Now we are going to calculate the formal charge on the double bonded oxygen atom. So the valency of oxygen is 6 and here it contains 4 lone pair of electrons. So 6 minus 4 minus half into the bonded pair of electrons. Between carbon and oxygen a double bond is present, so 4 electrons are there, half into 4. So the formal charge on the central oxygen atom is 0. Now we are going to calculate the formal charge on the single bonded oxygen atom on both the sides. So both the sides it contains the same number of lone pair of electrons. So the valency electron of oxygen is 6 minus the lone pair on oxygen is 6. So 6 minus half into bonded pair of electron. Between carbon and oxygen on the left hand side only one single bond is there. So 2 electrons. So the formal charge is -1. So next one is the nitrite ion, NO2 minus ion. So how to write the Lewis dot structure? So on the first we are going to write nitrogen. On the left hand side oxygen, a single bond is formed, and between nitrogen and the right hand side oxygen a double bond is present, and the nitrogen at the center is having a 1 lone pair, and the oxygen at the left hand side is having a 3 lone pair, and the oxygen at the right hand side is having a 2 lone pairs of electrons. So now we are going to calculate the formal charge on the central nitrogen atom. So the valency of nitrogen is 5 and it contains one lone pair of electron or 2 electrons. So 5 minus 2 minus half into the number of bonded pairs of electrons. Around nitrogen we have 3 bonds, so each bond contains 2 electrons, so half into 6, so that will give you 0. So the formal charge on the double bonded oxygen atom is 6 minus 4. The lone pair of electrons are 4 minus half into double bond is there, so it contains 4 electrons. So the formal charge on the doubly bonded oxygen atom is 0, and the formal charge on single bond oxygen atom is 6 minus, and it contains 6 lone pair of electrons. 6 minus 6 minus half into 2, that will give you -1. Now we are going to look into the next topic, ionic bond. How ionic bond is formed? Ionic bond, it is also called as electrovalent bond. Ionic bond is formed by complete transfer of one or more electrons from one atom to another. It is called ionic bond or covalent bond. So how ionic or covalent bond is formed? It is formed by a complete transfer of one or more valency electrons from one atom to another, and it is called ionic or covalent bond. Now we are going to look into the examples. Some of the examples are NaF, NaCl, CaCl2, MgO, calcium sulfide, sodium sulfide, etc. So now we are going to look into the example of the formation of ionic bond between sodium and fluorine. As you know, the electronic configuration of sodium is 281, and the valency shell contains 1 electrons. Now this 1 electron is lost or transferred to the fluorine atom. The valency shell contains only 7 electrons. Now the fluorine atom gets a configuration of 8. So now the Na plus ion and the F minus ion combine together to form a ionic bond. So sodium loses its outermost one electron and fluorine gains one electron to attain the stable octet configuration. So the next example is calcium chloride. You know the valency of calcium is 2. It is having 2 electrons and each chlorine is having 1 electron shortage, and 2 chlorine atoms combine, and calcium donates 1 electron to each of the chlorine atom, and calcium is converted into Ca2 plus ion and chlorine gets converted into Cl minus ion, and these two ions combine together and make a bond which is called ionic bond. The formation of ionic compounds primarily depends on the ease of formation of positive ion and negative ion from the respective neutral atom. So that is the atom, neutral atom, one atom should convert it into a positive ion and the other atom should convert it into a negative ion. So that is M in gaseous state gives M plus ion in gaseous state plus electron. Can you tell what is the name of this reaction? Which is nothing but it is a removal of valency electron from the outermost shell, and the energy required is called ionization enthalpy. The next one is an atom should gain an electron and become an anion. So X plus electron gives X minus and the energy is released and it is called electron gain enthalpy. So for example, in the formation of ionic bonds, it is favored between metals of group 1 and 2, which is having lowest ionization enthalpy, and non-metals of group 16 and 17, which are having highest electron gain enthalpies. In other words, an ionic compound or ionic bond is formed between a metal having low ionization energy and a non-metal having high electron gain enthalpy. The electron gain process may be exothermic or endothermic. The ionization enthalpy, on the other hand, is always endothermic because energy is needed to remove an electron. Ionic bond will be formed more easily between elements with low ionization enthalpy and elements with high negative value of electron gain enthalpy. So now it also depends on the electronegativity difference. Since a complete transfer of an electron from a less electronegative atom is required for the formation of an ionic bond, the electronegativity difference between the atoms forming the bond must also be appreciably high. So that is, between the cation and the anion, the electronegativity difference should be higher. The next term is lattice enthalpy. Higher lattice enthalpy leads to greater stability of ionic compounds. So when the lattice enthalpy is high, the stability of the ionic compound is greater. Lattice enthalpy is a direct measure of attraction between ions in an ionic solid. So once again I'll repeat, lattice enthalpy is a direct measure of attraction between ions in an ionic solid. Now we are going to calculate the lattice enthalpy of sodium chloride crystal. So the lattice enthalpy of NaCl is minus 788 kilojoules per mole. It is having a cubic structure and each sodium atom ion is surrounded by 6 chloride ion and each chloride ion is surrounded by 6 Na plus ions. So what are the properties of ionic compounds? Ionic compounds exist as solid in solid state. In crystal structure, the ions are arranged in a regular pattern. They have high melting point and high boiling point. They are soluble in polar solvents and insoluble in non-polar solvents. They are good conductors of electricity in molten state and aqueous solution. Ionic reactions are fast, so does not exhibit any isomerism. Can you tell why NaCl is a bad conductor of electricity in solid state? In the solid state, the Na plus and Cl minus ions are not free. Hence, it will not give rise to any conductance. So can you tell why AgNO3 gives a white precipitate with NaCl solution but not with carbon tetrachloride CCl4? The answer is NaCl is an ionic compound due to ionization in polar solvent water. So Cl minus ions are produced which combine with Ag plus ions of AgNO3 to form a white precipitate of AgCl. But the carbon tetrachloride CCl4 being a covalent compound does not give rise to Cl minus ions by ionization to form a precipitate. So can you tell which leads to the stability of ionic compound? The stability of ionic compound is due to the high lattice energy. So can you tell why ionic crystals dissolve in water? So many ionic crystals dissolve in water because water decreases their inter-ionic attraction in the crystal lattice due to solvation. So can you tell when ionic bond is favorable between two atoms X and Y? So the answer is X. Atom X should have low ionization energy and atom Y should have high electron negativity or electron gain enthalpy. So now we are going to look into the lattice energy in crystals. So what is lattice energy? The energy released when the requisite number of positive and negative ions combine to form 1 mole of ionic compound is called lattice energy. I will repeat. The energy released when requisite number of positive and negative ions combine to form 1 mole of ionic compound is called lattice energy. So ionic compounds in the crystalline state consist of orderly 3-dimensional arrangement of cations and anions held together by Coulombic interaction energies. These compounds crystallize in different crystal structures determined by the size of the ions, charge of the ions, their packing arrangement and other factors. So example is NaCl. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to energy released in the formation of the crystal lattice. So even though the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of a crystal lattice. Now we are going to look into the topic resonance structures. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, position of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid, which describes the molecule accurately. So now we are going to take the example of ozone. In writing the canonical structure of ozone, in the first case, we are going to write a single bond between the oxygen on the left hand side, a double bond is on the right hand side, and the bond angle is 116.78. And in the second structure, the left hand side, oxygen and oxygen are connected by a double bond, and in the right hand side, the oxygen and oxygen are connected by a single bond. The single bond length is 148 picometer and the double bond length is 121 picometer. So these two are the canonical forms of ozone molecule. Now we can write the resonance hybrid of ozone molecule by writing a dotted line between oxygen and oxygen on both the sides. So this indicates the double bond is delocalized over all the 3 oxygen atoms, and the structure 3 is called as the resonance hybrid of the ozone molecule. And the bond length in the resonance hybrid oxygen-oxygen bond length is 127 picometer, which is in between the single bond and the double bond oxygen-oxygen bond length. Let us look into some more information on resonance. Resonance stabilizes the molecule as the energy of resonance hybrid is less than the energy of any single canonical structure. So, when you write the resonance hybrid will be having lesser energy than any one of the canonical structure of the molecule. The resonance averages the bond characteristics as a whole. Thus, the energy of the ozone resonance hybrid is lower than either of the 2 canonical forms. The canonical forms have no real existence. The molecule does not exist for a certain fraction of time in one canonical form and for other fraction of time in other canonical form. There is no such equilibrium between the canonical forms. The molecule as such has a single structure, which is the resonance hybrid of the canonical forms, and which cannot be depicted by a single Lewis structure. We are looking into the example of carbonate ion. How to write the canonical structure? So we have already studied how to write the Lewis dot structure of carbonate ion. So in that we have considered a double bond at the middle. Carbon and oxygen is having a double bond. But now we can write different canonical structures So on the left hand side, carbon and oxygen may have a double bond, and other two oxygen gets a single bond. In another structure, at right hand side, the carbon and oxygen gets a double bond, and the other two carbon and oxygen gets a single bond. So totally we can write three canonical forms, and the resonance hybrid of all the three can be written as, so a carbon which is connected by three single bonds with three oxygen atoms, and we can write dotted lines for all the three carbon oxygen bonds, indicating that the double bond is delocalized over the entire molecule. In the same way, we can also write the canonical structure for nitric acid. So can you tell what is the bond angle in ozone molecule? It is 116.78 degrees. Now we are going to look into the polarity of the bonds. In reality, no bond in a compound is either completely covalent or ionic. So even if you take a covalent compound, no bond is completely covalent, or in any ionic compound, no bond is completely ionic. In reality, no bond in a compound is either completely covalent or ionic. When covalent bond is formed between two similar atoms, for example in hydrogen, oxygen, chlorine, nitrogen or fluorine, the shared pair of electrons is equally attracted by the two identical nuclei. Such type of bonds are called non-polar covalent bond. So can you tell what is non-polar covalent bond? So in this case, between oxygen and oxygen, the shared pair of electron is present. The shared pair of electron is equally attracted by both the oxygen atoms. Hence, it is called a non-polar covalent bond. But in case of heteronuclear molecules like HF, the shared electron pair between the two atoms gets displaced more towards the electronegative atom fluorine, and the electronegativity of fluorine is far greater than that of hydrogen. Thus, resultant covalent bond is called polar covalent bond. So, polar covalent bond is formed when the two atoms are having greater difference in electronegativity. So, now fluorine attracts the shared pair of electron towards itself, and it gets a partial negative sign, and hydrogen gets a partial positive charge. As a result of polarization, the molecule possesses the dipole moment, which can be defined as the product of charge of any one of the pole and distance between the poles. So what is dipole moment? It is a product of charge of any one of the poles and the distance between the poles. So now hydrogen gets a partial positive charge, and fluorine gets a partial negative charge. So the dipole moment is given by the formula mu, which is equal to E into D. E is the charge and D is the distance between the two charges. So dipole moment is usually expressed in D by units. 1 D by unit is equal to 3.33 into 10 power minus 30 coulomb meter. Dipole moment is a vector quantity, and it is denoted by a small arrow with tail on the positive center and head pointing towards the negative center. So dipole moment, it is a vector quantity, and we are indicating this by a small arrow with tail is on the positive center and head pointing towards the negative center. So in the case of HCl, the arrow head will be towards chlorine and the tail will be over the H+. Now let us look into the dipole moment in polyatomic molecules. In case of polyatomic molecules, the dipole moment not only depends upon the individual dipole moments of bonds known as bond dipoles, but also on the spatial arrangement of various bonds in the molecule. So in polyatomic molecule, the dipole moment not only depends on the bond dipole, but it also depends on the spatial arrangement of various bonds in the molecule. The dipole moment of a molecule is a vector sum of the dipole moment of the various bonds. So now let us look into the example of water molecule. So in the case of water molecule, the two hydrogen is bonded with oxygen atom, and can you tell which is more electronegative, hydrogen or oxygen? The answer is oxygen is more electronegative. So oxygen attracts the shared pair of electron towards itself. So the bonded electron pairs are pulled towards oxygen molecule. So in this case, the resultant dipole moment is given in the direction along this oxygen atom. Now we are going to look into the next example, BF3 molecule. So boron trifluoride, it contains 3 boron fluorine bond length, and the fluorine is more electronegative than boron, and the shared pair of electrons are pulled towards the fluorine atom. So now it is a vector quantity. When you add all the 3 dipoles together, the total dipole moment comes to be 0, because the bond angle between the boron and fluorine atoms is 120, and they cancel each other. So the resultant dipole, it cancels each other. So next is the carbon dioxide molecule. In carbon dioxide molecule, the carbon is doubly bonded to oxygen atom, and oxygen is more electronegative, and the dipole are in the opposite direction to each other, and hence the resultant dipole is 0. Now we are going to look into the special case, the dipole moment in ammonia. So in the case of ammonia, it is a pyramidal molecule with nitrogen at the center, and nitrogen is having 1 lone pair of electrons. So now the lone pair of an electron and nitrogen is having a moment which is in the upward direction. So now we are having in ammonia molecule, the nitrogen is more electronegative than hydrogen. So the shared pair of electrons are pulled towards nitrogen atom. So when you add all the 3 dipoles, and the resultant dipole is in same direction as the lone pair dipole. So now they added with each other and to give a resultant dipole moment in ammonia. Now we are going to look into the example NF3. So in the case of NF3, so now the hydrogen is replaced by fluorine. So now fluorine is more electronegative than nitrogen. Now the bonded electron pairs are pulled towards fluorine, whereas in the case of ammonia, the bonded electron pairs are pulled towards nitrogen. Here the case is reverse. So now the resultant dipole in the case of NF3 is in opposite direction to the dipole of the lone pair. So now the dipole moment of the lone pair and the bond dipoles of NF bond are in opposite direction. Hence, the resultant dipole will be lesser than in the case of ammonia. The resultant dipole moment in ammonia is 4.9 into 10 power minus 10 coulometer, whereas the resultant dipole moment in NF3 is only 0.80 into 10 power minus 30 coulometer. The reason here is the bond dipole and the lone pair dipole are in the opposite direction in the case of NF3. So fluorine is more electronegative than hydrogen. It is expected that the net dipole moment of ammonia should be greater than NF3. The resultant moment of NH bonds adds up to the bond moment of the lone pair, whereas that of the 3 NF bonds partly cancels the moment of the lone pair. So can you tell which is a polar covalent molecule? Oxygen, nitrogen, fluorine, HCl. The answer is HCl. What is 1 d by? So 1 d by is 3.33 into 10 power minus 30 coulomb meter. So which is the unit to calculate the dipole moment? 1 d by is 3.33 into 10 power minus 30 coulomb meter. So now we are going to look into the Fajon's rule. So according to this Fajon's rule, no bond is 100% ionic or covalent. So if you take a purely covalent compound or purely ionic compound, the bond is not 100% covalent nor 100% ionic. So to predict the nature of bond formed, Fajon introduced some empirical rules. The following rules are used to predict a bond with more or less ionic nature. With increase in cationic size, the ionic nature of the bond increases. So as the cationic size increases, ionic nature of the bond increases. So Li plus is smaller than Na plus, smaller than K plus, smaller than rubidium plus, then cesium plus. So next statement is, the smaller the size of the anion, more is the ionic nature of the bond. So the last case we have seen, the increase in cationic size, ionic nature of the bond increases. Smaller the size of the anion, more is the ionic nature of the bond. So NaF is greater than NaCl, NaBr is greater than NaI. So when the size of the anion is smaller, the ionic nature of the bond is higher. Ions, cation or anion or both, having smaller charges favors the formation of ionic bond. The third rule is ions, whether it is a cation or anion, having smaller charges favors the formation of ionic bond. So if you see NaCl, MgCl2, AlCl3, SiCl4, NaCl and MgCl2 are ionic in nature. Cation with inert gas configuration forms ionic compound. So cation with inert gas configuration form ionic compounds. The cation with pseudo inert gas configuration favors covalent bond formation. So example, Na plus Cl minus has a inert gas configuration, but Cu plus in CuCl has acquired pseudo inert gas configuration. So now let us look into this. Sodium ion, the configuration is 2,8. It has lost one electron. In the case of copper ion, the electronic configuration is 2,8,18. So according to Fajon's rule, the covalent character is most favored in smaller cation and large anions. This you have to keep it in your mind. So covalent character is most favored when the cation is smaller in size and anion is larger in size. So can you tell which is more ionic, NaF, NaCl, NaBr, NaI? The answer is NaF. So why? The smaller anion will prefer ionic character. Now we are going to look into the next concept, VSEPR theory. So what is VSEPR theory? Valency shell electron pair repulsion theory. Now we are going to look into some postulates of this theory. Lewis concept is unable to explain the shapes of the molecule. The VSEPR theory provides a simple procedure to predict the shape of the covalent molecules. This theory was proposed by Sidgwick and Powell in 1940. It was further developed by Nihlholm and Gillespie in 1957. It is based on repulsive interaction of electron pairs in valency shell of the atom. So again I will repeat, it is based on the repulsive interaction of electron pairs in the valency shell of the atoms. So the main postulates of VSEPR theory are: the shape of a molecule depends upon the number of valency shell electron pairs. The pairs of electrons in the valency shell repel one another since their electron clouds are negatively charged. So the pairs of electron in the valency shell repel each other since their electron clouds are negatively charged. The valency shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another to minimize the repulsion. So how we are going to consider the valency shell? So the valency shell is considered as a sphere and the electron pairs are locating on the spherical surface at maximum distance from one another to minimize the repulsion. These pairs of electrons tends to occupy such position in space that minimize repulsion and thus maximize separation between them. So now how to arrange these electron pairs? So they occupy the position in space so that they experiences minimum repulsion and maximum separation between them. A multiple bond is treated as a single electron pair and 2 or 3 electron pairs of a multiple bond are treated as a single superpair. So I'll repeat, a multiple bond is treated as a single electron pair and 2 or 3 electron pairs of a multiple bond are treated as a single superpair. Where 2 or more resonance structures can represent a molecule, the VSEPR model is applicable to any such structure. The repulsive interaction of electron pairs decreases in the order. So the lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So in other words, the repulsion is least in the case of bond pair and bond pair electrons, and the repulsion is maximum in the case of lone pair and lone pair electrons. Why lone pairs repel more? While the lone pairs are localized on the central atom where whereas the bonded pairs is shared between two atoms. So the reason is the lone pair is present only on the central atom, whereas localized on the central atom, whereas the bonded pair is shared between two atoms. As a result, the lone pair of electrons in a molecule occupies more space as compared to the bonding pairs of electrons. So due to the repulsion between the electron pairs, bond angle reduces. So in the case of ammonia molecule, the HNH bond angle is 107.3 degrees. Whereas in the case of methane, without any lone pair of electrons, the bond angle is 109.5 degree. So from 109.5 degree, the bond angle gets reduced to 107.3 degree in ammonia due to the repulsion. So can you tell the number of lone pair of electrons in methane, ammonia and water respectively? So the answer is in methane there is no lone pair, and in ammonia 1 lone pair, and water 2 lone pairs are present. So can you tell what is the order of repulsion of electron pairs? Lone pair is greater than lone pair, which is greater than bond pair. So now we are going to look into the applications of ESEPR theory. Geometry of molecules in which the central atom has no lone pair of electrons. So first we are going to look into the geometry of molecules in which the central atom has no lone pair of electrons. So based on the number of electron pairs, we are going to determine the geometry. So if the number of electron pairs is 2, then the geometry, molecular geometry is linear. So example is their central atom is at the A, is at the center, and two atoms are bonded to each other, BAB or AB2. So here the central atom is A and the two other atoms are B, and the bond angle is 180. It is a linear molecule. So examples of are BeCl2, BeF2, MgCl2, MgF2, HgCl2, etc. So can you tell what is the first type? So first type is AB2. First type is AB2, where the number of electron pair is 2, the bond angle is 180. Examples are BeCl2, BeF2, MgCl2, MgF2, HgCl2. The second type is number of electron pairs are 3. The formula is AB3, and the molecular geometry is trigonal planar. The bond angle is 120 degrees. Example is BF3, BCl3, ALF3, ALCl3. The next type is the number of electron pairs are 4, and the molecular geometry is tetrahedral. So A atoms at the center and the B atoms are at the corners of the tetrahedra. The bond angle is 109.5 degree. Example methane, carbon tetrachloride. The fifth type is AB5, the trigonal bipyramidal structure. Here the bond angle is, we have two types of bond angle. So one is BAB bond, which is 90 degree. So another BAB bond, which is 120 degrees. So PCl5 also has 180 degree bond angle. Example is PCl5. It also has. The next example is octahedral, AB6. So here the bond angle is 90 degree. So the examples are SF6 and tellurium fluoride, TeF6. So now we are going to look into the geometry of some simple molecules or ions with central atom is having one or more lone pairs of electrons. So now the molecular type is AB2L. So the bonding pairs is 2 and the lone pair is 1. The arrangement of electron pair is at the central atom. So the one lone pair is present at the central atom. The shape of the molecule is bent shape. The arrangement of electron pairs gives trigonal planar arrangement, and the shape is bent. Example is SnCl2, PbCl2. The reason is lone pair bond pair repulsion is much more as compared to the bond pair repulsion. So the bond angle is reduced. The next type is AB3L. The number of bonding pairs is 3 and the number of lone pairs is 1. So the geometry corresponds to tetrahedral and the shape of the molecule is trigonal pyramidal. So here the example is NH3. So the next type is AB2L2. The number of bonding pair is 2. The lone pair is also 2. The shape is tetrahedral. The arrangement of electron is bent. So example is water. So the next type is AB3L, so which contains 4 bonding pair and 1 lone pair, and the arrangement of electron gives trigonal bipyramidal, and the shape of the molecule is seesaw. So the examples are SF4. Seesaw type, the example is SF4. The shape is seesaw and the geometry is trigonal bipyramidal. The next type is AB3L2, 3 bonding pairs and 2 lone pairs, and the geometry of the molecule is trigonal bipyramidal and the shape is T-shaped, and the examples are ClF3. So the next type is AB5L, the 5 bonding pairs and 1 lone pair of electrons. The geometry corresponds to octahedral and the shape is square pyramid. So example is BRF5. The next type is AB4L2, 4 bonding pairs and 2 lone pairs, and the geometry is octahedral and the 2 lone pairs are present above and below the A atom, central atom. The shape of the molecule is square planar and the example is XeF4. So now we are going to look into the demerits of VSEPR theory. So it is not necessary to remember the shapes of all the molecules. Only electronic configuration is required to draw the shape of the molecule. So the main merits of VSEPR theory is it is not necessary to remember the shape of all the molecules. Only electronic configuration is required to draw the shape of the molecule. The total number of valency shell electron pairs in the center atom can predict the geometry of the molecule. The main demerits are VSEPR theory failed to explain the shapes of isoelectronic species. According to VSEPR theory, the shape of the molecule is based on the number of valency electrons. IF7 and TEF7 minus both have 56 valency electrons and are predicted to be pentagonal bipyramidal. However, the electron diffraction data and X-ray diffraction data reveal that the equatorial fluorine atoms are not coplanar. The VSEPR theory failed to explain the shapes of transition metal compounds. SeCl62-, TiCl62-, BrF62- are supposed to be pentagonal bipyramidal according to VSEPR theory, since the center atom have 7 electron pairs. However, due to the stereochemical inert pair effect, these molecules are found to be regular octahedral because one of the 7th electron pairs is stereochemically inactive. It is not based on quantum theory. It does not helpful to predict the nature of molecules. Example, the magnetic character. So can you tell what is the shape of ClF3 molecule? The answer is T-shape. Can you tell what is the shape of IF7 molecule? So it is pentagonal bipyramidal. So now we are going to look into the theory based on quantum mechanics. Lewis' approach helps in writing the structure of molecules, but it fails to explain the formation of chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond length in the molecule like H2 and F2. It also gives no idea about the shapes of polyatomic molecules. VSEPR theory has been criticized for not being quantitative even though structurally accurate. To overcome these limitations, the 2 important theories based on quantum mechanical principles are introduced. The first one is called valency bond theory. The second one is called molecular orbital theory. First, we are going to look into the valency bond theory. It focuses on how the atomic orbitals of the atoms combines to give individual chemical bond when a molecule is formed. According to this theory, a covalent bond is formed between 2 atoms by the overlap of valency atomic orbitals of each atom containing one unpaired electron with opposite spin. So, it should contain one valency electron orbital with unpaired spin or in the spin in the opposite direction.